Um, Let me first share a laptop screen. So is my laptop screen visible to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Before we start today's lecture, let me tell one thing. Today we are going to cover elementary thing about diffraction, and so it won't take more than 30 minutes. Okay, and then next we'll cover or we'll study diffraction through one of the well-known experiments, like Newton's ring in interference. Similarly, there is a well-known experiment called um, single slit or multi-slit experiments. So we'll study the diffraction through single slit experiments. So that single slit experiments through which we will study diffraction tomorrow, because if we continue that, we'll not able to end up it. So what we can do, we'll cover the elementary thing of diffraction today, and tomorrow we'll discuss about single slit experiments. As I said, like through Newton's rings, we study the interference. Similarly, through single slit experiments, we'll understand the basic things or the theories behind diffraction. That means how the intensity distributes as you move away from the center of the, you can see the diffraction or the screen or whatever you can call, right? So that's, idea or roadmap for today's lecture. And once you finish these things, as I said, it won't take more than 30 minutes. We'll have, discussion, whatever we, in particular about Newton's rings, because, the last class we covered Newton's ring, extensively, and I did not get an opportunity to all of you to ask me questions. So today, if you have any doubts on Newton's rings, after this elementary of diffraction class, we'll discuss that. Is it clear to everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
This call is
So
now
let
being
me
recorded.
make it full screen so that we can have, better visibility. Okay. So again, I'll, reiterate about harmonic oscillator as well as, Newton's rings experiment. So what we did, so that we looked at a group of examples before we, develop a statement, whether it is oscillator or waves or maybe interference and so on. So similarly, so before we give a statement about diffraction, we should look at what it actually is. So and as you can see, right, the phenomenon of bending and spreading of light or the edges of an obstacle is known as diffraction. So, so the light should bend, and it will not only bend, it will also spread. And how this happens? This happens because we have an obstacle, and around the edge of the obstacle, so this phenomenon occur, and that known as diffraction. So then immediately one immediately question may be coming in your mind, that how come light will bend? So far as we know that light can always travel in straight path. But how come light can
Sir,
bend?
can you just please go down little? Sir, just go down little. The image. Yes, sir. This no.
So that I'm coming. That I'm coming. Okay. So first, here we are saying that everybody knows that light will travel in straight path. How light will bend, right? So it is not possible. But in fact, it is possible, but it's in a different context. For example, the light that comes from the distant stars, and when it passes across, let's say, sun or let's say some heavy object, what will happen? So the light will bend. So the light will interact with the gravitational field of an object. It could be a star, sun, or heavier objects. It could be some other heavier objects. So light can actually bend. So those who knows about general theory of relativity, so there the light can actually bend when it passes across or close to a heavy star. Okay, for example, sun or maybe some other heavy star. So light can actually bend, but here we are not discussing in that context. We are discussing that how come light will bend? Because as far we know, light can only travel straight path. And if it will bend, so how it will spread so that we can have diffraction phenomena. So that we need to understand. So the first question, as I said, how light will bend? Or does light actually bend? As I said, yes, light actually bends, but in other context, as I said, the interaction between the light that comes from from very far away, maybe some other galaxies, or maybe let's say very far distance that we measure through light by light year. And when it passes across or close to a heavier star, it actually bends. That's its light bend. But in fact, light does not bend. So here, when you say light bend, in what context light will bend, and what kind of spreading? In other words, what will happen due to spreading of light? If we answer this question, then probably we can understand this statement. Or this statement we can develop through this, example that, like, as I said, we have already done for, harmonic oscillator, waves, interference, and so on. So let's look at these, examples or simply experiment, and then we'll have this statement. So now, as you can see, we need a, three objects, or you can say in experimental language, three apparatus. One is called source. You could have monochromatic light, and then we have an obstacle, which has, let's say, sharp edge like this, and then we have a screen. By the way, you can hear me, right? Am I audible?
Yes, sir.
Yes, sir.
Okay.
Yes,
So
sir.
now, light will come, and you can see here, it emits spherical wavefront. What does it mean, spherical wavefront? And immediately, again, one question might be strike in your mind. Then what other kind of wavefront one can get from source? Source means that emits light, as you know, coherent source. So we can have two different type of wavefront. One is called spherical, that emits from the point source, and another is line source that emits either plane wavefront or cylindrical wavefront. So what does it means? Can we have example? Yes. So if you have a point source, let's say like this, what will happen? The light will travel outward, and what we can see that the light will travel outward, and since it is a three-dimensional object, then at a given time t, so the light, since it will travel in all three possible directions, x, y, z, and if you join them, then we'll get a sphere. So therefore we have a spherical wavefront. And if you have a line source like this, what will happen? Then you can consider that each point over this line, we have infinite number of point sources. So therefore, they will emit like this. Okay, and similarly, this direction, so on. And if you join it, then what will it will trace a sphere? Sorry, the circle of top and bottom, and then we have cylindrical wavefront, right? So it will expand into cylindrical. So then you might ask question, okay, so we understand point source will always emit spherical wavefront and line source will always emit cylindrical wavefront. But how this plane wave will come? So if someone, an observer is nearby, then he or she will observe what? The cylindrical wavefront. And if an observer is far away distance, very large distance, what will happen? Then the surface of the cylinder, when it will reach, what will have? Then this will appear as a plane wavefront. So this is also true. If one observer is standing very far away, then this spherical wavefront will also turn as plane wavefront, right? Because the curvature will reduce and eventually it will be straight. So therefore we have plane wavefront. So what we learned that that point source and line source will emit spherical wavefront and cylindrical wavefront respectively. If an observer is observing this light, the wavefront that coming from this light source, very far distance, then the observer should notice the plane wavefront rather than spherical or cylindrical wavefront. Okay, so assuming this is a point source, so therefore we have a wavefront in all direction as I have given here. So one of the beams, light beams, that will touch the top part of obstacle which has sharp edge, and you can draw the line like this, right? And since we have obstacle, then it won't able to pass. And you can also draw the line like this, and since there is no obstacle, then the light can hit on the screen, then we have bright portion. What we are talking about, this line. Okay, and what will happen, that this light, since light travels straight path, so it will hit at the point A on the screen. Yes, S prime is the screen. So again, I would like to repeat, whenever you are drawing a schematic diagram and using some notations or symbols, you have to mention them clearly. Otherwise, they don't make sense. So I have written down here, SS prime stands for a screen, and so on. L stands for an obstacle with sharp edge. A stands point source of monochromatic light. Okay, so now the light will hit here A, but if someone will observe closely around this point A, that means up and down, and in fact the portion that below, which starts below the point A downward, for example AS prime, this must be geometrical shadow region, because the shadow of this obstacle does not allow that light will fall here. Therefore, it is geometrical shadow region. So similarly, the portion of the screen that starts from the point A upward, that means AS, is a lighted portion of the screen, right? Because we don't have any geometrical object, therefore it should be lighted portion, and it must have intensity I naught, which is the intensity that coming from this point source. So this will be intensity I naught, and that would be intensity 0. But if someone will observe carefully, right? So that the intensity, that 0, will start from M prime to S prime, not that start from A downward. So for M prime to S prime, the intensity will be 0. Similarly, the intensity I naught will start from M to S rather than A to S. So it means the portion mm prime, that means around this point A, the intensity is neither maximum nor minimum. That means not 0 nor I naught. It fluctuates between 0 and I naught. And that is known as diffraction, and it happens due to the diffraction phenomenon. So that I've written there. So and around the point A, that is mm prime, fluctuation of intensity 0 less than I naught, and it is an observation. Okay, and since in principle the am prime should be geometrical shadow region here, and that should be intensity 0, but it is not 0. Similarly, this am prime should be lighted portion and intensity I naught, but it is not actually I naught, it fluctuates. So as if the light has bent and entered the geometrical shadow region, that means am prime. So in that context, it is called the light has bent, because in principle am prime should be geometrical shadow region, intensity 0, but am prime is not 0, the intensity is not 0, it fluctuates between minimum and maximum. Similarly, am prime. So combining this, whatever we'll observe from this experimental setup, then we can formulate a statement that like as if light has bent and entered to the geometrical shadow region. And then it is not only entered, it is some observations. So therefore, as I said, that we can have this statement: the bending of light, because instead of a lighted portion, you can see still A to M prime, as if light has bent and it has spreaded around this point A, and therefore the fluctuation of the intensity we observe, which is known as diffraction. Is it clear to everybody? Am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay, so now we understood what is a spherical wavefront, plane wavefront, cylindrical wavefront, but we did not explain how light travels. So now nowadays we understand light is an electromagnetic wave. It might not require an underlying medium to travel. So therefore, it can travel like the electric and magnetic field, they oscillate perpendicular to each other. Therefore, light travel. But in old time, right? So that time, one scientist called Huygens. So we have, that will study Huygens principle. So that, but actually how light actually travels in a medium. Okay. So by the geometrical approach, by following Huygens principle, we can construct the wavefront, right? So how we'll have spherical wavefront, cylindrical wavefront. Actually, what would be the exact diameter of the spherical wavefront, or surface area of the spherical wavefront, how fast it can travel. So that we'll also study probably in the next class. But for the timing, we remember it will have spherical wavefront or cylindrical. If an observer is observing very close, and if an observer is standing very far away from the source, either it is a point source or plane line source, he or she must observe plane wavefront rather than spherical or cylindrical wavefront. Okay, so now what we learned that three objects, or you can say items, or in experimental language, three you can say apparatus. So three items are involved in the process of diffraction. One is source, the second one is obstacle, as I said, called apparature, and third one is called screen. And then depending on their relative position or location, the diffraction pattern can be divided into two groups. So what are they? One is called Fresnel class of diffraction, and the second one is Fraunhofer class of diffraction. So as I said, so this classification is due to the location of the source screen with respect to obstacles. So when source and screen, if they are placed at finite distance from the apparatus, So then we call Fresnel diffraction. However, if these two things, namely source and screen, are not, at finite, if they are at infinite distance, then we call Fraunhofer class of diffraction. And as you can see that I have written down here, effectively at infinite rather than writing infinite, because infinite, infinite is meaningless, right? So therefore, we have, effectively infinite. In fact, we'll have some optical, devices that will, in principle, make it infinite. In that sense, we call this infinite. And then you might ask question, of course, since since the source and screen they are at finite distance, so therefore it is much easier to control Fresnel class of diffraction rather than Fraunhofer diffraction. But the truth is, reverse way. That means the Fraunhofer class of diffraction is easier to obtain compared than a Fresnel diffraction. Okay, and it is due to that the effectively distance and that easy to achieve. Then the question is how. The thing is that by using two convex lenses, we can make effectively at infinite distance both source and screen with respect to apparatus. So therefore, we have a great control of these two, this couple of convex lenses, and hence it is very much easier to achieve. So that I have written down here. So let's, L1 is the fast lens between source and apparatus, and L2 should be in the second lens, and let's say it has focal length or focal distance f2, and it has f1. So f1, and this is f2. So the second lens must be placed in between screen and apparatus. And how we'll put, as I've written down here, that the first lens which is kept in between source and apparatus, so it must be its focal length f1 from the source as represented by the schematic diagram. So we have a source, apparatus, and the screen, and here the first lens L1, right? And it must be it has to be put in such a way that the distance between the source and this lens must be the focal length of this lens L1. Similarly, the second lens L2 must be put in such a way that the distance between the second lens and the screen should be the focal length of that second lens F2. Okay, and you can see this diagram that I will explain. So by using this couple of lenses, we can push both source and screen towards at infinite, effectively infinite distance compared than apparatus. And since we have a couple of lenses, and by adjusting these lenses, we can have a great control over this Fraunhofer class of diffraction compared than Fresnel class of diffraction, and hence it is easy to achieve that diffraction. Okay, so how we can push source and screen towards infinite, effectively infinite, as you can see from this schematic diagram, right? We have point source, and then because we have lens, since the distance is focal length f1, then the other side we should have parallel wavefront or parallel beams. Okay, because if you incident a set of parallel beams, then it must converge at a focal point. And in the reverse way, if we keep the source at the focal point, other end or other side of the lens, we must have set of parallel beams. And then these apparatus will see the set of parallel beams. So do remember that, as I said, when the distance between a source and an observer is very, very large or at infinite distance, then the observer will receive the parallel or plane wavefront from the source. So, hello, am I audible?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. So now, as you can see, since by putting this fast lens, we can effectively push the source towards infinite. It is not actually infinite. Since we are receiving the parallel wavefront and which falls here on the operator, so therefore, as I said, the parallel wavefront one can obtain the plane wavefront one can obtain when the source is at very large distance, at infinite. So putting the fast lens, we push the source effectively towards infinite. So similarly, we have a parallel wavefront, right? And here it converges here. Okay. So therefore, what I know reverse way, that if we keep source here, what we'll have? Then the operators will see what? That parallel wavefront. That means again the distance between operators and this screen is uh, effectively infinite due to the second lens L2. So now this concept is clear, how we can push both source and screen towards infinite by using a couple of lenses. Okay, and as I said, since we have great control over these lenses, so therefore we can replace the source, or we can vary the source distance. So therefore, and similar, we can adjust the lenses. And in that regard, we have great control over another class of diffraction compared to the Fresnel class of diffraction. So it is easier to achieve. So therefore, in the next class, as I said, we will study the theory of diffraction by using single slit. Okay, and in fact, this is single slit experimental setup. Again, we'll discuss tomorrow, right? And the single slit diffraction experiment, it falls in the group of or class of Fraunhofer class of diffraction. So that, as I said, we'll study the diffraction theory through Fraunhofer class of diffraction using single slit experimental setup. That we are going to discuss in the next class. So this is all about elementary of diffraction, and so if you have any quick question, you can ask me on diffraction. Hello, any questions on today's lecture? Am I audible?
Yes, sir, audible.
Yes, sir. Audible.
Okay, any question?
No, sir.
Sir, the lighter portion, I didn't get the lighter portion and unlighter portion, shadow portion of the
Okay,
that.
so you are saying about this figure, right?
Yes, sir.
Okay, so let me again draw it by using different color. So the light beam will come from this point source. Okay, as I've
Yes,
drawn
sir.
here this, and it will hit where? The point A. Okay, and since we have this geometrical object, it must have some shadow, and in principle from A to S prime it should be shadow region, or you can say the geometrical shadow region. Due to the geometry of an object, the shadow will appear accordingly. Since we are representing two dimension, two dimension, if you have a three dimension, it will have some thickness, so accordingly you have a shadow regions. So AS prime should be your shadow region, whereas A to upward, AS for example, it must be lighted portion. But what we actually observe when we perform this experiment, so so this case, what we'll have, that actually this AM portion, which must be geometrical shadow region, so this portion, so this must be geometrical shadow region. This is not actually the completely dark, that means the intensity is not actually 0. It means dark, intensity 0 means dark, so it is not 0, right? It is not completely dark. Similarly, the AM portion is not completely bright, that means not I naught. Okay, it is in between 0 to I naught similarly. So overall, the portion around this point A means M prime, that means the both side of the screen, this portion where the intensity fluctuates, and that phenomena is not diffraction. Got it? And M prime S prime should be completely dark. The M prime S prime, the intensity will be 0 as I said, so therefore it's actually shadow region. Similarly, AM to S is completely bright where the intensity equal to I naught. But MM prime, that means the portion around this point A, the intensity fluctuates. So in that regard, I said this AM prime, which should be geometrical shadow region, but it is not actually the shadow. Is it clear?
Yes, sir.
So any more question? Okay. So yes, I have already increased in it. So any more question on today's lecture?
Excuse me, sir.
Yes.
Sir, would you please take the slide down? Actually, on the next slide, I have some doubts
Okay.
in the diffraction part. Yes, sir. Yes, sir. In this part, sir, the parallel light are in
So
only
that
one
I'll
direction,
explain. That
but
I'll explain.
while
Okay.
diffraction.
So when we'll talk about single slit experiment, that I'll explain why it bends, right? That I'll take. As I said, Huygens principle that we'll discuss in next class. Okay. And in fact, what Huygens principle says that if you have wave front, so we can have a wave front here. Wave front comprises large number of point sources. And since we have a point sources, the light can emit in all directions, not only this direction. We have a beam like this, 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 and so. And this is one of the beam, right? So similarly, this source all direction, one component will be parallel to this one. That actually from the Huygens principle that we'll discuss in the next class.
Okay, sir.
And there will be also in a state, right? The straight one without any deviation. Right, straight one, which will hit here. So this will be the center of your screen or the center of the diffraction pattern. Oh, I can say. So all those things we'll discuss in the next class.
Okay, sir.
So any more question? Okay. So the next is, do you have any questions on Newton's rings lecture that we discussed last class?
Yes, sir. The proof x equal to r square by 2r.
Okay, let me close these things. Let me save it. Let me open. So is it visible?
Yes, sir.
By the I got a message from some from one of you regarding the lecture 8. Somebody said actually this lecture 9 it comprises couple of lectures, 8 and 9. Since I completed in one lecture, and in fact, if you go through the video lecture, I think what happened? I can see. Okay, so it is very long lecture. The lecture 9 comprises lecture 8 as well as lecture 9. Okay. Okay, just a moment. So this proof.
Yes, sir. This.
So how many of you have done this? Anybody has done it? Anybody has done it? You see,
Yes, sir.
you
Yes,
see,
sir.
some students they have done only geometrical, configurations, right? And you'll draw an imaginary sphere. Okay. So what you have to do? So you will draw an imaginary sphere. Do you able to see me?
Yes, sir. Yes, sir.
And then we have, let me use some different color, this one. And then we have a center R, center. And then this, we are talking about this point. This point B, right? This, and this will be capital R, the radius of curvature. Yes or no?
Yes, sir.
Yes, sir.
And then you can have, if you draw a straight line from here to here, it will be diameter. So let me give this C. Is this color visible to all of you, or I'll use some different color? Okay, so this is C, and what I can do, I can draw a chord that should be perpendicular to this diameter. B to B prime. Okay. So so now what would be this distance? Anybody can tell me?
R minus R cos theta.
Okay, now this will be T because this is the thickness T, right?
Oh.
And this distance?
R minus T.
Capital R minus T.
No, this will be 2R because this is R, na? RR plus 2R, right? So 2R minus T. Okay, so this distance should be 2R minus T. Got it? Okay, then you use the triangle principle that I'm not going to do. Okay, and what is this? What is this distance? Please go to mute mode. What is this?
This is the radius of the
Small r.
Newton's ring.
Radius of the Newton's ring.
Newton's ring.
So now you know the triangle principle, and then you must have this relation. That I'm not going to do. So those who have done, they must have followed this principle. Yes or no?
Yes, sir.
Yes,
Yes,
sir.
Okay.
Thank you, Varus.
So if you follow these things, as I've written down here, you must have this relation. Small r square equal to 2rt minus t square. From the property of triangle, I can say from the properties of not only triangle, many triangles, what we can have r square equal to 2rt minus t square. You must have this relation. Okay, and you get the triangle. For example, We have already this triangle. Let me use some different color, probably black one. We have this triangle CB. Let's say this is B prime. Let me give different color. This is, you have a C. This is, let's say, B. This is B prime. This one is B, and this is, let's say, this is already, let's say, O prime, right? And let's say this is M. So now we have a triangle CBM, and we have also this large triangle. This one, O, sorry, it is not. So this big triangle OBM, right? CBM, OBM, and then you can use the triangle principle. You will most of this relation. Got it? Yes or no?
Yes, sir.
Hmm? So those who have asked this question, did you understand how to do it? Yes or no?
Yes, sir.
You use the property of the triangle, right? And then you must have this relation. For example, you will end with that BM multiplication BM multiplied at MB prime will be what? This O prime multiply with MO. I have already told, right? You prove it. BM multiplied with MB prime equal to OM multiplied with O prime. Got it? So BM multiplied with MB prime will be O prime multiplied with, that MO multiplied with MO prime multiplied with MO. That I written. MO multiplied with MO prime. So BM, what is a BM? Sorry. Actually, you can use the property of triangle. What will obtain that MB prime equal to MO multiplied with MO prime. So MB equal to T into T. What is MO? Is T, and what is MO prime? 2R minus T. That is our this. So this, sorry, this must be R. So this implies R square equal to 2TR minus T square. Got it? So now your job is to prove that how we'll get this relation by using the property of triangle. Got it?
Yes, sir.
Okay. So those who have done, they must have followed this principle. Yes or no?
Pythagoras,
Yes, sir.
MBC.
We used Pythagoras theorem.
Theorem. Then you can use, right, that
In triangle CMB.
MBC.
MBC CMB in that triangle.
So that from just triangle principle, you must have this relation, I think, or you can have this, and finally you must have this relation, or some other approach. You must have this relation. Okay.
Yes, sir.
Yes, sir.
Okay. So any more question on Newton's rings? Okay. So if somebody will ask you question, so instead of monochromatic light, if someone will use polychromatic light, so what will happen this ring structure? Anybody? Anybody can answer?
So I
Am I?
can choose the different
Yes.
colors.
yes, we have a colors. But what will happen? Will it affect the diameter of the Newton's rings? Will it affect the intensity of the Newton rings, or will it affect other things?
Diameter, sir.
Yeah.
The diameter will be affected because lambda will change.
Okay, yes, lambda will change, and then if you are using monochromatic light, the intensity variation will be very, sharp. You have a maximum and minimum. That means if you move from one ring to another ring, then we'll get the center completely dark and at the center of the bright ring completely bright or white. But if you use polychromatic light, you won't observe completely dark ring, you won't observe completely bright ring because it will be superimposed of multicolors. So the sharpness of the peaks will be affected. That means a decrease, or you can say the intensity will also decrease, and then the diameter of the any particular ring, for example, let's say 20th ring or pth ring, will either increase or decrease depending on the wavelength associated with the polychromatic light because it comprises many wavelengths. Okay. So any specific question? Okay, let me ask you one more question. What will happen to the diameter of the Newton's rings? Let's say in particular ring, let's say pth ring. Okay, let's say pth ring, or in particular, let's say 20th ring. What will happen to the diameter of the 20th ring if we use some transparent liquid, or instead of air flame, we have liquid flame? Anybody? Do you able to hear me? Yes or no?
The diameter will decrease.
Why? Yes, it will decrease, but why? Why the diameter will decrease? So if you use liquid, medium that I have not, given. So this one, right? You must have derived. So this case, the refractive index of the medium mu will appear. Will it multiply or you have to divide it under this relation? Anybody has derived? Will
So
it
we will
be?
have to divide.
We have to divide.
It will be 1 over mu or these things. It is 1 over mu, and since the refractive index of any liquid is greater than 1, right? So therefore, the diameter will decrease rather than increase. Got it? By using this principle, you can, as I said, you can calculate the, this refractive index of any medium, transparent medium, where one can observe, the Newton rings, and can measure the refractive index of that medium. Okay. So if you have no further question, I think we should stop here, and we'll meet tomorrow. That means in the next class to discuss about single slit experimental setup and the theory behind the Fraunhofer class of diffraction. Okay. Bye everyone.
Thank you, sir.
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 Thank you, sir.